Okay, we'll see now another concept is the bulk modulus concept. So I'm directly coming to the topic, bulk modulus. So what does it mean by the bulk modulus? We'll see here. If any change of the pressure, if some volume change is occurring, that means if you consider one fluid element, initial it was under the atmospheric pressure. Now we are giving some extra pressure over it, del P. Because of this extra pressure, some volume change is taking place. Because of some extra pressure, some volume change is taking place. So what is the volumetric strain? So volumetric strain means how much volume changes is occurred and what was the initial. That is the volumetric strain. This volume change, why it is occurring? What is the reason of this occurring? Because of the extra pressure. As you are giving the extra pressure delta P, then the volume change is occurring delta V. Then the concept of the bulk modulus is coming. The bulk modulus can be defined as the K or E. Some books they are mentioned by K, some books they are mentioned by E. That will be equal to the delta P divided by volumetric strain. One negative sign should be there. Why the negative sign? Because if you apply the pressure, the volume will be decreased. Because if you apply the pressure, the volume definitely will be decreased. That means the relationship is like that. If you increase the pressure, the volume will be decreased. If you decrease the pressure, the volume will be increased. That's why this negative sign will compensate this. And this value is always positive values. It's always a positive. So what is the unit of this thing? Unit of bulk modulus. That is the unit of the pressure divided volume by volume, no unit. So unit will comes like the pressure unit. The pressure unit and bulk modulus unit are the same. It can be defined as the Pascal bar in this way. Newton per meter square, kilonewton per meter square in this manner. Now here, this delta P by D. So another with the volume, the density. What is the relationship of the density? So density relation we have seen, the density is the mass divided by the volume. A simple manner we are writing it here. Now the M can be written as the density into the volume. After taking the natural log in the both sides, ln M, ln delta, and again differentiation here both sides. We differentiate in both sides. It will come as the mass is our system is a control mass system. A system inside a system, the mass conservation will be preserved always. So no change of mass. So if you differentiate this thing, it will comes always 0. But density changes will be takes place. So what would be the density changes? It can be written as the delta. Similarly, will be by 3. So here d delta by delta can be written as the dE. In this way, if your term in terms of the limiting terms, it can be written as the limiting way also. Some significant way. If you write this thing can be written in this way also. dP dV by UP. So hence we are doing this thing. So our values of K, bulk modulus values, can be written as the dP divided by d rho by rho, or rho dP by d. This is the way to write it. Now the condition of the incompressible flow, if you want to see. So what is the bulk modulus? From bulk modulus we are getting these values. So rho into dV by. What is the condition we are taking? The flow is a incompressible flow. So incompressible flow, the density variation is not significant. Density variation is not significant. That means the d rho by rho, if less than 5%, we can consider the flow as a incompressible flow, or fluid as a incompressible fluid. Incompressible flow and fluid is a something different nature. Incompressible flow, in that case, we are considering this thing. Simple thing is zero. But it is not possible. Where there is no volumetric strain, this kind of the flow is taking as the considered as the incompressible. No volumetric strain. This kind of the flow we are considering as the incompressible flow. But it is, if in terms of the density we are talking about, there must be some change of the volume and the density due to such cases. And if this change is negligible, that means less than 5%, we are considering it is sufficiently, it can be considered as the incompressible. Now, the concept of the, from one equation, you will see the next chapter, Bernoulli's equation, where it is saying that the pressure, the change of the pressure is some more convertible with the velocity. So if you change the pressure, it will be converted into the velocity. We're getting from the Bernoulli's equation. For the case of the so many application in the nozzle, in the diffuser, you will see in the nozzle, at the expense of the pressure drops, the velocity is increasing. The same concept. If we change the pressure at the expense of the pressure, we are getting some velocity. In the diffuser, that is the opposite. At the expense of the velocity, we are getting some pressure. In terms of the velocity, means it's a kinetic energy. LP is the pressure, that is the kinetic energy per unit volume or consideration. This V is the velocity, not the volume. So this K, in terms of the order, we are writing it in terms of the order of the K. So that is the order of the density. Another this thing divided by the, in terms of order we are writing it. So here, order of d rho by, this d rho by rho we are taking in the side, left side. So it is nothing but the order of del V square by K. It's a order of half V square by K by rho. Now the term is K by rho. What does it mean? Is the C square. What is C? C is a sonic velocity or sonic speed. This concept is coming from Newton Laplace equation. Because the C from Newton's Laplace equation, from the C we are getting it, C is equal to E by rho. So it is nothing but half into V square by C square. So velocity divided by the sonic velocity. This velocity, actual velocity divided by the sonic velocity at any medium is known as the Mach number. Is known as the Mach number. We're writing it as a capital M. So half into capital M square. The concept is coming in this way. So what is the concept is coming here? You see, you the density, the order of the density, if you write it down in here. So what are, again, I'm showing you here, in terms of the density, you're writing it. So from the Bernoulli's equation, you could be able to see the pressure changes is the half rho v square. That means it is converted in terms of the velocity. So in the order, we are writing it here, and we are getting this thing. So ultimately, we are getting this thing. So ultimately, we are getting the things we're writing here. Del rho by rho. Order we both sides we are taking out. Order v square half by 6. So what is another way? Half m square and number square. Condition of incompressibility we have already discussed about just now. Less than 5%. That means if this less than 5%, that means we are trying it 0.05 half m square. That means the if Mach number. So if Mach number is less than root over of 0.1, so value is nearly 0.31. If the Mach number is less than 0.31, we can consider the flow as the, or fluid as the incompressible. We can consider if Mach number is less than 0.3. In the air, the sonic velocity, you might have seen that it is nearly 330 meter per second. It's nearly 330 meter per second. So if any vehicle velocity is 110 meter per second, so nearby air, we can consider this air as an incompressible during the calculations. So that is the way. So this is the most important thing. The change of density divided by the density should be less than 5%. That is the consideration. And bulk modulus concept, again, bulk modulus, okay, in terms of the density, if you're writing it down, so you are writing here rho. Now the pressure versus rho, there is a change. What kind of changes will be there? Pressure and rho, we'll see it in the next topic. The thermodynamics, the isothermal process. The thermodynamics, the isothermal process means, so write the formula here, Pv is equal to mRT, ideal gas equation. So rho R. For the case of isothermal, this RT is a constant. So P by rho is a constant for the case of the isothermal. So for the case of the isothermal, P by rho is a constant. So some P is equal to some constant component, constant, let you take it C into rho. If we differentiate this, dP C into d rho B divided by d rho, C is nothing but P by rho. C is nothing but P by rho. So your bulk modulus at isothermal case, isothermal bulk modulus KT, we are writing it as the rho into E by rho is equal to pressure. The same pressure gives you the bulk modulus in case of the KT. It is the isothermal bulk modulus. On the other hand, if you are considering on the other hand, here isentropic process or adiabatic process, reversible adiabatic process we known as the isentropic process. The isentropic process, what is that consideration? In isentropic process, PV to the power gamma is equal to constant. So PV to the power gamma is equal to constant. We can write it down P by rho to the power gamma is equal to CS. Because M into, if you change it mass by density, it will get it. Mass is a constant quantity. Constant mass system, that's why. Now here P is equal to some constant into density to the power gamma. If we again differentiate this both sides, it will comes in this way, gamma into rho to the power gamma minus 1 into. So dP by d rho gives you C dash gamma rho. So what is C dash? C dash again the same thing. You can put it here P by rho to the power gamma. So gamma into E by. So hence the bulk modulus at isentropic bulk modulus will be equal to that rho gamma E by, and gamma into. Hence you could be able to, as gamma is greater than is equal to 1 always, because gamma is known as the Cp by Cv. That constant pressure specific heat divided by the specific heat at constant volume. So Cp is always greater than the Cv. That is the purpose. So we can say that the isentropic bulk modulus should be always greater than the isothermal bulk modulus. If any multiple choice question they're asking this question, you can really say. And it is nothing but Ks by Kt is nothing but in this way. That is a consideration in here regarding the isothermal bulk modulus. So we'll see one problem and we'll finish this topic here. There is one IS problem. It is but in very easy format it is given to you. Just an analysis. When the pressure on a given mass, so you see here the mass is constant. Always they're telling it the given mass of the liquid. Constant mass is telling about. Is increased from 3 megapascal to 3.5 megapascal. Your density is changing here from 500 to 501. So as you increase the pressure, your density changes is also occur. So what is the average value of the bulk modulus of the liquid over the given pressure range? So what is the change of the pressure here? Del P, the change of the pressure. Change of the pressure is 3.5 final minus 3, so 0.5 megapascal. Change of the pressure. What is the change of the density? Density changes. So density changes 5 not 1 kg. So here del rho by rho will gives you 1. What was the initial density? Initial density was 500. So it is very easy. Just you apply the formula here. Del rho by rho. So 0.5. So it will gives you the so your answer becomes in this way. The very simple question comes in IS. This kind of the question maximum they will ask you regarding the bulk modulus topic.